guys. So today we're going to talk about applying empirical formulas to some different situations. The first thing we'll do is review a straightforward empirical formula problem. Then we will apply an empirical formula to a hydrate problem and then to a combustion problem. So let's take a look. And I apologize if it looks like I'm not making eye contact with you. I have a double monitor system here, and so I'm looking up at my monitor. All right, so here's our straightforward empirical formula problem using mass data. We have a sample of a compound containing 24 grams of carbon. So I like to start off by just writing what I have. 6 grams of hydrogen. Oh, forgot my sig figs there with the carbon. And 8 grams of oxygen. It's hard to write small with these Bluetooth writing tablets. What is the empirical formula? Pretty easy here. We are going to convert to moles by dividing by the molar mass. So we know that carbon is 12 grams. Oh, that shouldn't say carbon there. That should say hydrogen. That should be an H. Hydrogen is 1 gram per mole. And oxygen is 16. Just making sure I remember correctly. All right, 24 divided by 12 is 2 moles of carbon. 6 divided by 1 is 6 moles of hydrogen. And I don't know why that just popped up there. And 8 divided by 16 is 0.5 moles of oxygen. Okay, now we are going to divide everything by the smallest molar amount, which is oxygen with 0.5. So we're going to divide everything by 0.5. So that means for carbon, we get 4. For hydrogen, we have 12. And for oxygen, we have 1, because 0.5 divided by 0.5 is 1. All right, so we just bring those ratios down into our formula. Carbon 4, hydrogen 12, oxygen 1. And that is our empirical formula using mass data. Let's look at our next problem here. Oh, gotta erase my screen. All right. So here we have using a hydrate. All right, so washing soda, a compound used to prepare hard water for washing laundry, is a hydrate, which means that it has moisture in it. It has molecules of water attached to the original washing soda, which means that a certain number of water molecules are included in the solid structure. Its formula can be written as sodium carbonate hydrate, and X is the number of moles of water per mole of sodium carbonate. When a 2.58 gram sample of washing soda is heated at 25 degrees Celsius, all the water of hydration is lost, leaving 0.948 grams of sodium carbonate. And we call this an anhydrous sample because it is dry. So what is the value of X? So the first thing we need to do is figure out how much water we have lost. So we take our mass of our hydrate, which is 2 0.558 grams, and we subtract our dry sample, or anhydrous, by 0.948 grams. And the difference there is 1.61 grams of water. So that's how much water is in that hydrated sample. All right, so next up, we want to know how many moles this is. So we take 1.61 grams and we divide that by the molar mass of water, which is 18.02 grams per mole. And we get 0.0887 moles of water. All right. Next up, we want to find out how many moles of anhydrous sample we have. If the weight includes a container, if it's saying the sample inside the container weighs such an amount, now we want to subtract the amount of the container out because we're not going to include it in calculating moles, right? It doesn't matter for finding out how much water is lost because the container would be in both the hydrate and anhydrous samples. Excuse me. But if we do have a container, now we do want to subtract that out. Okay, so we're going to calculate the molar mass of the anhydrous sample. So we know that our anhydrous sample weighs 9.48 grams, and we're going to divide that by the molar mass of sodium carbonate, which the molar mass of sodium carbonate is, I'm going to write that over here, 105.98 grams per mole. So we're going to divide by that amount here. And that's going to give us the number of moles of sodium carbonate anhydrous. And that number is 0.00895 moles. Okay, then our next item is that we are going to take our moles of water and get our ratio or proportion of water to moles of anhydrous sample. So we're going to take that 0.0, checking my numbers. What is that? Oh, that's an 8. 8. I know my handwriting is not as neat as if I were writing on a whiteboard here. Moles of H2O over, how many do we have? 0.00895 moles. Notice we're keeping our 3 sig figs there of our anhydrous, 2CO3. And when we divide, we get that there are 10 moles of water for every 1 mole of anhydrous sample. So we would rewrite our formula as Na2CO3 with our very large dot there, 10 H2O. So now we know how this is written, that for every 10 moles of water, actually it's better said, for every 1 mole of sodium carbonate, we're going to have 10 moles of water attached. Okay, now we're going to look at empirical formula with a combustion problem. The characteristic odor of pineapple is due to ethyl butyrate, a compound containing carbon, hydrogen, and oxygen. The combustion of 2.78 milligrams of ethyl butyrate produces 6.32 milligrams of carbon dioxide and 2.58 milligrams of water. What is the empirical formula of the compound? And then we have a little bit of part B there, but we're not doing part B. We're just going to do this part. Okay. So the first thing that we're going to do is we're going to use our amounts of product to figure out how much reactant we started with. So we're going to start with carbon dioxide. And so let me grab my writing tool here. So I'm going to start way up here because I'm going to need a lot of room. So we have 6.32 milligrams of carbon dioxide. Oh, nope, I grabbed my writing tools. Don't do that. Carbon dioxide. And we are going to divide by 1,000 milligrams to get into grams. And then we are also going to divide by the molar mass of carbon dioxide, which is 44 grams. And so when we do our calculations, we realize that we have 1.44 times 10 to the negative 4 moles of carbon dioxide. Now, there's one carbon in carbon dioxide, so we have a 1-to-1 ratio of moles of carbon in moles of carbon dioxide. So that means that we are producing in this combustion reaction 1.44 times 10 to the negative 4 moles of carbon, because it is a 1-to-1. There's one carbon atom in carbon dioxide. All right, so that was number one. So next up, we are going to determine the moles of hydrogen from the water produced. Okay, so we have how much? We have 2.58 milligrams of water. We're going to divide by 100 milligrams per 1 gram to get that into grams. And then we are going to divide by the molar mass, which is 18.02 grams per mole. And we realize that we have produced 1.43 times 10 to the negative 4 moles of water. Now, in water, we have 2 hydrogen atoms for every 1 mole of water. So that means that we need to multiply by 2. So 1.43 times 10 to the negative 4 times 2 means that we have 2.86 times 10 to the negative 4 moles of hydrogen. Bloop. All right. So now we need to figure out the amount of oxygen, and we're going to do that by converting the moles of carbon and hydrogen that we have discovered are in our reactant into moles. We're taking those moles and converting them into grams so that we can subtract them from the original amount. And that leftover amount is going to be our amount of oxygen, which we will convert into moles, and then we will subtract. So here we go. So we know that we have 1.44 times 10 to the negative 4 moles of carbon. And we are going to not, I've just been dividing so much, I automatically wrote divide. We are going to multiply, as we're going back 2 grams, we are going to multiply by the molar mass of 12 grams per mole. And we are also going to multiply by 1,000 to get back. Oh, no, we don't want to multiply by 1,000 yet. We want to stay in milligrams for now. I was getting ahead of the game. We want to wait. We want to keep it in milligrams. So, so we do need to multiply by 1,000 because we want it to be in milligrams and it's in grams. See, I'm showing you to make sure that you do it the right way. Okay, so we're going to multiply our moles by our molar mass and then by 1,000 because we want it to be in milligrams, and we end up with 1.73 milligrams of carbon. Let's do the same thing with hydrogen. So we know we have 2.8 times 10 to the negative 4 moles. Sorry, my handwriting is a little messy here. It's the digital tablet. And we know that that is 1 gram per mole that we are multiplying by, and then we are going to multiply by 1,000 to get it back into milligrams. And that gives us 0.289 milligrams of hydrogen. Yeah, that's an H. You know it. All right, so we go back to our original amount. Where is it? Combustion of 2.78. So 2.78 minus 1.73 milligrams of carbon minus 0.289 milligrams of hydrogen gives us 0.77 milligrams of oxygen. Well, now we want to know how many moles of oxygen that is. I know a lot of conversion problems here. That's why the ability to convert numbers is so important. So if we have 0.77 milligrams, we need to divide that by 1,000 milligrams to get into grams. And then we need to divide that by, what's the molar mass of oxygen again? 16. Yes, 16 grams per mole. And that is going to give us 4. Whoa, that's messy. Let's do that again. 4.8 times 10. Oh my gosh, so messy. Slow down. 10 to the negative 5th moles of oxygen. Okay, hold on. I just can't leave it like that. Let's see. No, that wasn't the eraser. This is the eraser. Ooh, that's going to be big. A little better. Whew. Messy, messy. That's a multiplication. Okay. Okay, guys, so our final step is to take the moles of carbon, moles of hydrogen, and moles of oxygen and divide them by whichever one is the smallest. So because this is a little messy because I'm using the Bluetooth writing tablet, I have highlighted my moles of carbon, moles of hydrogen, and moles of oxygen in red here so that they stand out a little bit. If I was writing on the whiteboard at school, it would be a little different looking, right? And so we're going to divide all of those by the smallest one, which is oxygen, at 4.8 times 10 to the negative 5th. And when we do that, we get a 3 to 6 to 1 ratio. So that means we have 3 carbons, 6 hydrogens, and 1 oxygen. And we see our final empirical formula down here at the bottom.